Firstly,
Can you
I
hear
would
now?
like to introduce the contents,
Okay.
include motivation, related work, overview, implementation details, experimental results, conclusions, and future work. Now comes to our motivation. As well known, sculpture is an important part of culture, which has been widely used for thousands of years. We all know that relief is a kind of sculpture artwork which is carved into a surface. The length proportion of figures in relief is mentioned, and the contours of shape approximate the painting, so it can be classified as high relief, bas relief, and sunken relief. In recent years, with the rapid development of 3D technology, generating digital relief has a very important application in decoration environments and promoting culture. Therefore, how to automatically generating bas relief with high aesthetic value has become a problem for researchers. As you can see from picture, to mimic bas relief production with multiple characters is fairly arduous by inputting a 3D model, with the resulting popularity of 3D printing and personalized customization. Procedure methods for automate relief layers are needed, and it would be tedious and impractical to model massively multi-model relief manually. Relief generation can be classified as two-dimensional image-based relief generation and three-dimensional model-based relief generation. But there are some limitations of two-dimensional image-based method. It is difficult to extend image-based relief generation to high relief generation as images contain insufficient height information and the computation time is much greater. Recently, proposed models-based bas relief generation techniques have become more mature in terms of algorithm adaptability and relief effects. However, for the relief editing, they do not consider the relief layers, which limits the aesthetic value of their results. The layered design is our most important work in this paper. This figure is an overview of our bas relief generation method. The method that we present in this paper achieves this goal in two steps. First, we identify the evaluation indicators of the bas relief arrangement on top of the photographic composition literature and the wearable bas relief work. This step is performed only once in advance, acting as a pre-processing. Then we realize these evaluation indicators, which are collected by manually labeling the relief datasets. Given an arbitrary initial layers, optimizing it subject to human factors is not an easy task. To address this issue, in the second step, the initial layers is adjusted iteratively by minimizing an object function that accounts for the evaluation indicators. We optimize the overall object function using semantic annealing, which is formulated with the weighted geometry mean combined model. Now I will explain the implementation in details. Firstly, we collect 200 images of bas relief layers from the internet to build the dataset. Then, based on photographic composition rules, the literature, and the center evaluation indicators, we extract the evaluation indicators that can affect the bas relief layers, such as project area, location of bounding rectangle, curvature, separation distance, occlusion area, height difference, and symmetry. Here we can see the schematic diagram of the effects of layers based on the different evaluation indicators. Then we explain how to model the evaluation indicators, which are collected by manual labeling and statistic methods. We learn from classifying relief pictures, extract the factors that influence the relief, and then build the evaluation indicators as shown in these pictures. We adopt the adaptive mixed Gaussian function to fit the Gaussian functions of some evaluation indicators. Note that we simply set the fixed value for the projected error ratio indicators. The adaptive performance is to determine whether the variance of the fitted function and the given curve is greater than the given threshold, thereby achieving the piecewise Gaussian fitting. Our relief layers problem is formulated as a combinational optimization problem. A combination of all items from the list of candidate indicators are found to best satisfy both the photographic composition and the aesthetic rules. To quickly obtain the suitable solution, we explain the classical heuristic search algorithm. Simulated annealing, which is commonly used in furniture arrangement and building layers planning. We first define the objective function in the heuristic process using the evaluation indicators, and then construct the simulated annealing model. In our approach, we random choose one direction and change its currently position to another, as shown in this picture. However, one of the disadvantages of the processing scheme is deadlock. It means when the movement distance is too large, the model will move to the same position repeatedly, while a small movement distance can cause a slow convergence. So we set a random value of movement distance for each iteration, so as to avoid these situations. And in our experiments, the range is from 10% of the side length of the mapping region to 1% of it. Additionally, to avoid the models moving beyond the boundary, we will examine the distance of the movement before changing the configuration. This figure shows some of the target objects we used in our experiments. The regions surrounded by the blue lines are the mapping regions. We can see that the first column, which shows the models with a flat line shader, and the second column, which shows the models with a wireframe shader, and the third column, which shows the seed wheel of the models. This figure illustrates the comparison of the convergence of different objective functions. We count the number of iterations required for different object functions to achieve the layered optimization score. The horizontal axis represents the number of the iterations, and the vertical axis represents the value of the objective function. The figure A shows the objective function value of two models arranged on a plane. The left of figure A is the linear model, and the right of figure A is the geometry mean model. As the figures show, the geometry mean model can noticeably increase the convergence rate of the object function, and reduce the number of the iterations. So we use the geometry mean model in these experiments. Here are some experimental results. We can see that the first two columns show the layers of two models arranged on the sphere surface model. The middle two columns show the layers of the two models arranged on a complex target model. The last column in the figure shows the layers of one model arranged on a mask model. The first two false rows of the figure represent the initial configuration of the relief layers, which are generated using the random value of the evaluation indicators. The last row represents the final results of the relief layers. To illustrate the effectiveness of the base relief layers method, we compare the experimental results of the layers with the results, from which creates the appearance mimicking surface from the artificially designed three-dimensional scene. This method requires manual layouts of the three-dimensional scene models, which is time-consuming and unable to adapt to changing art trends. However, our method only needs to provide the source model and the target model, so that it can efficiently generate the base relief, as shown in the figure B. The figure A shows the results has obvious overlap in layouts, where our method enables a layout according to the defined indicators. In order to verify the effectiveness of our method, we do use a survey. We invited 60 undergraduate students to participate in the following questionnaire, which involved 7 cases in this figure. In each case, the participants evaluated 5 images of the base relief layers, including an image of the initial random layers of the base relief model. 3 layers images output during the optimization process, and the final model layers image. In the same case, 6 images are presented to the participant in random order, and they are requested to rate each image from a score of 1 to 5. We can see that our method enables 3 cases with the highest score in the 7 cases, and 6 cases with the top 2 scores, which demonstrates the effectiveness of our methods. As we know, the science of aesthetic and artistic is one of the most fundamental base relief qualities. In this paper, we have introduced what we believe to be the leading of automatic synthesis of base relief layers, avoiding manual and semi-automatic relief design methods, and consider in the comprehensive manner arrangement factors, photograph composition. This method enables users to better understand the creation process of base relief. In particular, we define a group of evaluation indicators of base relief arrangements, which allow us to assess the aesthetic of base relief theoretically. Extensive experiments and validation demonstrate that within the small number of the models, our method is able to produce robust, beautiful results. However, there are some limitations in our proposed method. It is only suitable for arranging a few models to generate the relief. Results consider the influence of the orientation of models on the user's cognition. In the future, we expect to combine the semantic information of the model for more logic layers. What's more, we will consider the more complex and realistic models and scene layers. Then we hope to achieve more progress in these Thanks for your attention.
Okay. I'm sorry. I cannot answer questions accurately. If you have any questions, you can send an email to the answer Jiahui. Thank you again.
Okay, thank you very much, Feiyu, for coming here, to present this video.